Hello everybody, get ready to do lesson 9.7 part 2 of pre-calculus math today. Animated PowerPoint math video at AOL.com for questions or materials. And for today's notebook, you got 8 points. We'll go into your notebook guide, name, date, period, students, and then into our classwork sheet, you have 32 points. Due date here for my onliners and homeschoolers, have that fill that in. And then today's bell work, we have find the value of the trig function given that u and v are in quadrant 4 and u equals -3/5 and cosine v equals 1/radical 2. So we have sine u minus v, and then we have cosine u minus v. Teachers, give your students 5 minutes, pause your video for 5 minutes, and check back for the solutions. Okay, for today's solutions, so today's bell work, students, sine u minus v. So sine u minus v as a trigonometric identity would be sine u cosine v minus sine v cosine u here, 4/5, will equal this once you plug in your values here. And then you end up with radical 2/10, 1/5 times radical 2. When you rationalize this, you end up with 10 for 79. And then for 80 here, cosine u minus v, again, we plug in our values here. Cosine u here is 4/5. Multiplied by 1/radical 2 plus -3/radical 5, multiplied by -1/radical 2. And then this comes out to 7/5 times radical 2. Rationalize your denominator, and you end up with 7 times radical 2/10. So students, you should have that. Self-assess yourself. And let's move on. Okay, in the next example, you were asked to find a polar equation for a specified conic. To do this, let P be the distance between the pole and the directrix. So, number 1, horizontal directrix above the pole, and you're going to have an equation like this: R equals EP over 1 plus E sine theta. So that's what you're going to have as an indicator of your horizontal directrix above the pole. And then a horizontal directrix below the pole, you're going to have R equals EP over 1 minus E sine theta. You'll know that immediately. And then for 3, vertical directrix to the right of the pole, you have EP over 1 plus E cosine theta. And then vertical directrix to the left of the pole, it'll be R equals EP over 1 minus E cosine theta. So these are fast and easy indicators of how your graph is going to look. So let's try one. We have finding the polar equation of a conic. Find a polar equation of the parabola whose focus is the pole and whose directrix is the line y equals 3. So you can see that the directrix, so we have a directrix here is y equals 3. Here's your directrix here. Here's your parabola. Find a polar equation of a conic. So we have a parabola that's shaped like this, and here's our directrix here. You can see that the directrix is horizontal and above the pole. Moreover, because the eccentricity of the parabola is E equals 1, which means it is a parabola, and the distance between the pole and the directrix is P equals 3, so P equals 3 here, you have the equation R equals EP 1 plus E sine theta will be the same thing as 3 over 1 plus sine theta with these characteristics here. Okay, so let's try one. Find a polar equation of the conic with its focus at the pole. So we have focus at the pole. We have a parabola. Eccentricity, of course, is 1. And then our directrix here is x equals -1. And then down here, students, this is yours, so tackle that. First, we're going to do this one up here. So this situation here, e equals 1, x equals -1, and p equals 1. So the vertical directrix to the left of the pole, we have to the left of the pole here. So r will equal 1 times 1 over 1 minus 1 cosine theta is what our equation here will be for this parabola. And then down here, students, this is for you to do. And let's move on. So we're going to get an application now. Kepler's laws, listed below, named after German astronomer Johannes Kepler, 1571-1630, can be used to describe the orbits of the planets about the sun. It's like, what? It's like, yep. Number 1, each planet moves in an elliptical orbit with the sun as a focus. 2, a ray from the sun to the planet sweeps out equal areas of the ellipse in equal times. And then 3, the square of the period, meaning the time it takes for a planet to orbit the sun, is proportional to the cube of the mean distance between a planet and the sun. How do you like that? So that's kind of cool situation there. So with that knowledge, although Kepler simply stated these laws on the basis of observation, they were later validated by Isaac Newton. He lived from 1642 to 1727. In fact, Newton was able to show that each law can be deduced from a set of universal laws of motion and gravitation that, given the movement of all heavenly bodies, including comets and satellites. So this is illustrated in the next example, which involves the comet named after the English mathematician and physicist Edmund Halley. So if you use Earth as a reference with a period of 1 year and a distance of 1 astronomical unit, which, by the way, an astronomical unit is defined as the mean distance between Earth and the Sun, or about 93 million miles. So that is an astronomical unit. Then the proportionality constant in Kepler's third law is 1. For example, because Mars has a mean distance to the Sun of 1.524 astronomical units, its period P is given by d cubed equals p squared. So the period of Mars is p equals 1.88 years. So we get into like a distance here. I would assume this is light years here. So the period of Mars is, and how do we define P? So the P here is d cubed. Okay, that is what a P is. Astronomical units, its period P is given by d cubed equals p squared. Okay, well, okay. What do anything? I don't know. So let's go into our example here. So Halley's Comet. Halley's Comet, and here is its elliptical orbit here for Halley's Comet. With an eccentricity of e equals 0.967, the length of the major axes of the orbit is 35.88 astronomical units for this length here. The major axes, 35.88 astronomical units. Find a polar equation for the orbit. So we need to find an equation for this orbit here. How close does Halley's Comet come to the Sun? So here's the Sun, here's our orbit around the Sun. Using a vertical major axis as shown, choose an equation of the form r equals EP over 1 plus e sine theta. So we have a vertical major axis here, so we know we're going to have a sine function in that. Because the vertices of the ellipse occur at theta equals pi over 2, which is down here, and theta equals 3 pi over 2. I'm sorry, this is 3 pi over 2, and then pi over 2 is up here. You can determine the length of the major axis sum of what? To be the sum of the r values of the vertices. Did you know that? That is 2a equals 0.967p over 1 plus 0.967 plus 967p over 1 minus 0.967, and when you add these together you get 29.79p, and then which equals 35.88, and then so p in this situation here in this approximation will be 1.204, and EP will equal 0.967 times 1.204, which will be EP will be 1.164. Using this value of EP in the equation, you have r equals 1.164 over 1 plus 0.967 sine theta. So there it is. Here's your equation of this ellipse there by using this r values here of the vertices. So that's pretty cool how you can, just from that value there, you can come up with a whole algorithm for this orbit. We're not finished yet. So r equals 1.164 or 1 plus 0.967 sine theta, where r is measured in astronomical units. To find the closest point to the sun, meaning the focus, substitute theta equals pi over 2 into this equation to obtain r equals 1.164 over 1 plus 0.967 sine pi over 2, which will come out to 0.59 astronomical units. So when you substitute this value in here, sine over pi over 2, you come up with this number here for astronomical units, which is 55 million miles. So the closest point to the sun is 55 million miles for Halley's Comet. So let's, bouncing off of that, let's go into a guided practice now. So the planets travel in elliptical orbits with the sun at one focus. Here's our sun here. Assume that the focus is at the pole, so we have a pole here. The major axis lies on the polar axis, which is here is our polar axis here, and the length of the major axis is 2a. So polar axis is actually here, pi over 2, and then our major axis is here. Show that the polar equation of the orbit of the planet is r equals 1 minus e squared a over 1 minus e cosine theta, where e is the eccentricity. Okay, so that's, you got a whole lot going on here. Okay, to use eccentricity when theta equals 0, r equals c plus a equals e a plus a, which will come out to a times 1 plus e. So, okay, we got that out of the way. Therefore, this a times 1 plus e will equal ep over 1 minus cosine theta. And then when we hash this out, when we isolate our ep here, we have this situation here. And then we have a times 1 minus e squared equals ep. Thus, r will equal ep over 1 minus cosine theta will equal 1 minus e squared a over 1 minus e cosine theta. So there it is right there. Show that the polar equation of the orbit is this here. And we just did that. It is 9.7 Part 2 Pre-Calculus Math. Here is my email for questions or course materials, animatedpowerpointmathvideo@aol.com. Thank you very much.